Okay, so today I'm going to talk about design and additive manufacturing of lightweight materials. So again, I'm assistant professor in the Department of Mechanical and Aerospace Engineering at UCF, and I joined UCF in 2017, and I'm currently actually direct additive manufacturing and intelligent system laboratory in the MAE department. So, so here is a little bit background about myself and my research. So again, actually before I joined UCF, I was a research senior research associate at Penn State, and then I researched my PhD degree in mechanical engineering at Georgia Tech. And my research interests include 3D printing, also known as additive manufacturing, data-driven or artificial intelligence assisted intelligent manufacturing, better health management, as well as condition monitoring, diagnostics, and prognostics. So today I'm going to focus on one of my research areas, which is 3D printing or additive manufacturing. So today I will only talk about two particular 3D printing techniques. In general, additive manufacturing refers to the manufacturing process of joining materials to fabricate or produce parts or components in a layer by layer fashion. And most people actually are familiar with additive manufacturing techniques already. And today, the two techniques I will cover, one is called selective laser melting, also known as SLM. So SLM uses high power density lasers to melt and fuse metallic powders together. And it can also be used to actually fuse polymers, but oftentimes it has been increasingly used to fuse metallic powders together. And the second 3D printing technique I will talk about is called fused deposition modeling. It uses a thermoplastic filament, which is heated to its melting point and then extruded in order to produce a part. So basic FDM is focused on 3D printing of polymers and composites. So the first project I'm going to talk about is design and fabrication of BioInspired light metals. So the motivation behind this research is that actually lightweight materials are very important and has a wide range of applications in various industries, such as aerospace engineering, automotive engineering, also energy, as well as defense industry. And these industries require not only lightweight, but also high performance or strong materials. And you may know actually composite is one of the lightweight materials, but sometimes composites are not strong enough. So in this case, we focus on design and fabrication of bio-inspired lightweight, but also strong metals. So as you can see from these slides, we actually designed and fabricated a few so-called lattice structures as shown right here. And you can see these lattice structures are quite complex. It's almost impossible to fabricate these complex lattice structures using conventional manufacturing processes such as milling, turning, or injection molding. And you can see we fabricated various different structures using so-called unit cells. And here I only show 4 different unit cell types, such as cubic diamond, cubic fluorite, and also tetrahedral octet edge. And these 4 unit cell structures actually are only 4 of many different unit cell structures. And these structures actually are inspired by honeycombs and also by actually crystal structure in chemistry. And these are only 2 out of 24 lattice structures we printed. And these lattice structures are made of aluminum alloy and magnesium alloys. The reason why we selected aluminum and magnesium alloys is because the density of these 2 alloys are very low already. And then we further optimize the structure itself in order to further reduce the weight and also increase actually strength to weight ratio. And for this particular project, we're interested in the compressive behavior or compressive strength of these different materials or lattice structures. So the goal is to actually customize or tailor or tune the mechanical behavior of these 3D printed lattice structures. So here I only show two stress strain curves of two 3D printed lattice structures with cubic diamond and tetrahedral octet edge unit cell structures. And you can see here, actually, these two lattice structures exhibit very different mechanical behavior based on the stress strain curves. So in other words, by varying the relative density of the lattice structure, as well as varying the unit cell type, we can tune or tailor the compressive behavior. And in this case, you can see they exhibit very different compressive strengths if you take a close look at the engineering stress. And also, we further observed the failure modes of these different lattice structures. Actually, they exhibit very different failure modes as well. So you can see, so these failure modes include crush, cracks, and buckling. And these are the 4 images we captured using the digital image correlation technique. So using this DIC technique, we can observe how these lattice structures fail during this compressive testing. The second project is about carbon fiber reinforced polymer composite. So again, we designed and fabricated this carbon fiber reinforced polymer composite using 3D printing process, which is fused deposition modeling. And also this carbon fiber reinforced polymer composite also have a wide range of applications in automotive engineering, aerospace engineering, and the defense industry. So for this in particular project, we actually designed and fabricated continuous carbon fiber reinforced polymer composite rather than more conventional composite, which is made of short fiber reinforced polymer composite. So by using continuous carbon fiber, we can significantly improve mechanical properties of polymer composite, and especially further improve or increase strength to weight ratio. And here you can see from these SEMI images, we can see these continuous fibers clearly. And the main objective of this approach is also similar to the first one. We want to further design and fabricate continuous carbon fiber reinforced polymer composite with tunable or tailorable performance. So here you can see we fabricate different amount of continuous fiber at different layer. So in this case, you can see this legend indicate the number of fiber rings and also in each layer, and also the number of fiber rings at different layers. So you can see we performed also mechanical test, in this case, tensile test, and we can tailor the tensile behavior by varying the amount of continuous fiber at each layer. So you can see we fabricated quite a few composites, and you can see they exhibit a very different mechanical behavior. So from this curve, you can see this plot, you can see some of them exhibit are pretty brittle, some of them are pretty ductile. So by varying the amount of continuous fiber, so we can tune the mechanical behavior. And from these DIC images, for the first 2 DIC images, so you can see we can observe crack initiation and a crack propagation and eventually failure. And this is a more ductile composite. For the last 2 DIC images, so this one is more brittle. So in other words, the failure basically happened almost all of a sudden, which is a more brittle property. So again, so by varying the continuous carbon fiber amount, so the volume fraction, we can further tune and tailor mechanical property of 3D printed continuous carbon fiber reinforced composites. So these are the 2 projects I'm going to cover today. And for future research and collaboration opportunities, For the near-term research areas, I'm going to work on 3D printing of new materials, such as biomaterials and also soft materials. For long-term research areas, I'm going to focus on understanding the stress process structure property relationships in 3D printed complex parts, as well as machine learning enabled material design for composites and also lattice structures. And for potential collaboration areas, I think I'm interested in working with people in the areas such as solid mechanics or mechanics of materials, material science, machine learning, sensing, and control. And at the end, I would like to acknowledge my funding agencies such as Digital Manufacturing and Design Innovation Institute, National Science Foundation. I haven't listed NSF here, but we received a grant from NSF about the battery health management. And also I would like to thank my collaborators from MAE and MSc departments at UCF. That's all for my presentation. Thank you.